Let's start. Firstly, there was a question just now that in the latest problem set, I have this. In addition to hard copy, you must enter your answers at this particular URL. And in case you're wondering why I'm doing that, so firstly, what you see, if you haven't bothered visiting it, what you see out there is a web form where you have to fill your name and student ID. And then when you continue, it basically asks you to fill out the answers that you came up with for the various problems. You have to fill those in. You can leave them blank if you have been unable to do. The idea is, since we have relatively short time before the grades and all get due, so I'm going to be doing some randomized grading out here, which is primary grading will be through this, and then very significant percent we are going to spot check, particularly those who do it all correctly. So that's kind of the whole intent. You still have to submit your hard copy, and you still have to submit both of them by the same deadline. So just want to make that clear. So you do have to fill this out.
Yes, it is submitted, and later on you find out mistake.
You submit again, there's a timestamp entry. I'm going to take the latest timestamp entry against your name. Okay? Unfortunately, you'll have to fill it out all over again. You cannot just selectively update from it. Any other questions on that? Okay, so second thing was this design homework number 4 that I kind of shipped around yesterday. So there's a question, will I take, if you do this and then your final score is higher than the score on this, sort of a tough luck situation in that case. You are making a commitment on the other. So if you submit it, then this would be the score that would be counted. What you can certainly do is, let's say you submit it and then you discovered that it is wrong or something, then shortly thereafter, if you tell me, discard my design homework, I will gladly do it, but no other. So it certainly cannot get into after the final. So that's kind of other. I also wanted to briefly go over what you have to do in this particular design assignment. It's actually a lot easier than the previous design assignment. So just so what's happening out here is that you are basically designing a little microcoded. Hello everyone. So what you're designing is a microcoded encryptor, but basically to keep your focus on just on writing the microcode, so I've basically provided both not just the test bench but also kind of other parts of the system. So what you have out here is, so there are two .circ files I have given. One is the test bench, and in the test bench what I have done is I have given to you a keyboard. This is where your system should be wired up, and then there is a dumb TTY output that Logisim provides. And just to show that how things might work out. So for example, if I were to just connect, let's say, keyboard data to data out, and I were to connect keyboard ready to D out ready, and then I were to, so basically this is kind of a null encryptor. The data is just kind of passing through from the keyboard. And if I were to now simulate, so let me set the frequency to something high, let's say 1 kilohertz. And now if I were to simulate, see, as I'm typing, you'll see the characters appearing out there. Okay, so this is so basically what the keyboard does is there's a buffer inside it. If the buffer is empty, then nothing comes out. But whenever there's a character, it basically outputs it for 1 clock cycle. And this particular line, keyboard ready, it will make it high if there's a character available, and the character appears out here. There is also a line called keyboard read enable, which if you assert to be low, then it ignores the clock. So it kind of does some equivalent of clock gating internally. And then also there's a keyboard clear. So kind of the idea is, since the keyboard presents the character only for a clock cycle, your encryptor is likely going to be slower. So you're probably going to have to manipulate this keyboard enable also so that the character kind of stays out there until you have processed it, then you let it go. So in any case, the entire I/O of the keyboard is available to you to make use of. As with the previous assignment, there's a reset signal which comes up high for one clock cycle at the beginning. And then on the right-hand side is the dump TTY of Logisim. It basically takes bunch of inputs. Again, clock and reset are kind of already wired up. Reset just cleans it up. There is D out and D out ready. And again, the idea is that whenever D out ready is high, and a clock edge comes, then D out is read in and displayed out here. So the idea again is that you should, whenever you want to write a character, you make put the character on D out and make D out ready high for one clock cycle. If you make it high for more than one clock edge, then multiple copies of that character will appear. So your encryptor typically would wait for the next character from the keyboard, encrypt it, and then take the encrypted one and output it. The one exception is that any non-printable characters should be passed straight through. So these are things like backspace and new line and things like that. So they just have to be passed through. So the assignment kind of describes that how printable ASCII characters are those which have a 7-bit hex code of 0x20 through 0x7e. Those characters need to be encoded. The encoding is being done using the simplest possible encryption, which is called Caesar cipher, which was used by Julius Caesar long ago, apparently. But the basic idea is that you are given a number, and you are going to shift along the alphabet the letter. So, like for example, let's say we were doing it just with the standard 26 letter English alphabet, A to Z. Let's say A to Z uppercase, and the key was 5. Then A will become B, C, D, E, F. So A plus 1, 5. So 1 plus, or if you say A is 0, then 0 plus 5, and that would become F with a key of 5. If the key is more than 26, then you will just wrap around. So after Z comes A. Now with the ASCII, what happens is you have all the letters from 0x20 to the code 0x7e. So you'll have there are 95 characters. So in effect, you have an alphabet of length 95, and you're going to wrap around at the end. Now again, sort of to make the task kind of meaningful, so that you just don't. This is my phone doing the Amber Alert. Okay. What I've also done is I have given to you. I've given to you the data path plus the high-level design also. So this is the other circ file, where basically what you see is things are wired up, and there are two modules, controller and data path. Data path is, I've designed the data path so that using some combination of operations over the data path, you can implement the encryption function. So if you go inside the data path, you would see that this data path has an adder. This is actually an 8-bit adder where I have 7 bits out here and a 1 bit out here. The two inputs to the adder are coming from muxes, which are 4 to 1 muxes. And the second operand to the adder can be inverted using this XOR gate. So if you recall, inverting the second operand and feeding a carry in of 1 results in a subtraction operation. So you can do subtraction using this. The 4 inputs for operand 1 are either coming from an input called D in A, which is one of the 8-bit input into a data path. It can also come from a constant value 20, hex 20, and hex 20 is actually the ASCII code for the first printable letter. It's chosen carefully for that. And then the other two inputs choices for operand 1 are 2 registers I have provided, R0 and R1, where you can remember things. And likewise for operand 2, it can either get it from D in B, which is a second 8-bit input into the data path, or it could be the constant 5f. 5f is actually 95, so it's a number of printable ASCII characters you have. So you'll have to think in terms of modulo operations around this. And then finally, the other two are again R0, R1. The output of the adder can also be loaded into either one of these two registers or both of them. So the load enabled signals for these two registers are brought out here, and your microcode has to control them. The output of the data path goes out into this line called dout. So whenever you're ready, your encrypted output will kind of go out here. And then you have signals which tell you something about that value. So you can check whether the result of the adder output, is it a 0, is it negative? So you can look at the MSB, that's the sign bit, flag sign, FSGN. You can check whether there was an overflow happen if you think of number as an 8-bit 2's complement number. And you can also check at the carryout. So you can do things like do some operation. If the result is negative, then jump to a different state than otherwise. So you have all these bits coming up. And again, if you go back to the top level design, you see they are wired up to the controller. In the controller, in the baseline design, you are only allowed to use a ROM and a register. You can pick the ROM to have any number of bits, and any number of data bits, any number of address bits, and your register can have any number of bits, but you cannot use any other logic. So everything has to be, so it's a pure microcode design. And you'll be graded by how big the ROM is and how many bits you use in the state register. There's an extra credit portion where using techniques we discussed in the lecture, such as microprogram counter and branch logic, the idea is you have to shrink the ROM size and you get 20% or 25%, whatever I've listed, as extra credit if you are able to reduce the ROM size. If your ROM size remains the same as the original design, you get 0 credit. So that's kind of the way that works. At the baseline level, this is really a programming exercise. Okay, you're given a data path with a known set of capabilities, and it's wired up for you. You would see that one input of data path is the key, which is coming from outside, and the other input of the data path is from the keyboard. The keyboard signal is coming into the controller, and all the outputs, those going to the keyboard or those going to the TTY, they're all coming out of your controller. So it's basically writing a program, very low level in terms of bits. You'll have to submit the contents of the ROM as well as, of course, the schematic, and test it out on a variety of cases. It's a very simple encryptor, so type some text and see whether it comes out right. Check it for different values of keys, and also check it for different clock speeds. Very slow clock speed as well as very fast clock speed. So that's what's happening, and first try to come up with the logic behind this encryption. So this notion of shifting the letter down the alphabet, think of how you can express it as a series of arithmetic operations, and those arithmetic operations are what you have to do. So that's what's happening. Any questions on this? Yeah.
Is ROM a type of register?
ROM, you can think of ROM as a whole bunch of registers plus some decoder for the address lines. Okay. So if I had a bunch of registers and I put a decoder in front so that I enable, I put a decoder in front and a multiplexer so that I read one of the registers out to the multiplexer. Okay, that's essentially what a ROM is. It's implemented differently because it conceptually can be a whole bunch of registers, so you don't design it the register. But yeah. Any other questions? Okay, so so let's go back to our timing stuff that we were doing. So last time around, we started on this timing issue and I kind of described that for combinational logic, there are two timing parameters which are of interest. One is the so-called propagation delay, which basically says what is the latest time from when the input stabilizes to when the output becomes stable. And then the other one was contamination delay. And contamination delay says from the first time that the input changed to what is the earliest time the output changes. And we'll see the role they kind of end up playing in a short while, but these are the two. And then we also talked about that how when you are making more complicated logic and you know the contamination delay and propagation delay of the components, then how you can create the one. And the idea is you enumerate all the paths from input to output, and you take maximum of all the propagation delays, maximum of sum of all the propagation delays along each path, and that will give you the prop delay for the whole circuit. And likewise, you find the sum of contamination delay for each path, and then take the minimum across all the paths, and that will give you the contamination delay. So we discussed that. We had some examples, and the first problem of the problem set is basically on that. I've given you a piece of logic and some of the delays. Now, what you're going to see is, go ahead. So it's defined here. Minimum delay is the minimum amount of time from an input signal change to an output signal taking its correct value.
It looks like the same as the propagation.
No. So look at the definition again, right? So it's the minimum amount of time taken, not the latest time. Okay?
The input should settle to the correct value, and output should also.
It's only saying it's minimum, not the latest. So this leaves open the possibility that output may change again before settling again.
But then it's not correct.
Huh? Then it is not minimum delay. Minimum delay, yeah, okay. So to a correct value. So imagine temperature changes. I have different copies of the same part. Some of them may be operating faster, some of them may be operating slower. So this is giving you across all parts what the propagation delay will tell you across all parts, under all conditions, what would be the delay. So some parts may see this value change settle earlier. Some parts, or for some input data values, you may see the input, the output settle earlier than others. So like for example, the adder may see a shorter value, one copy of the adder may have a smaller value than other. An adder may have a smaller value under different temperature conditions. Same adder for some input values may settle earlier than other input values. An adder may get a correct value, change again, then again go back to the correct value. So all of those things will fall under minimum delay. So propagation delay is the worst case situation. After that, across all conditions, you're guaranteed it will not change.
So for minimum delay, it says is the minimum amount of time from the input signal change to its correct value. Does that mean that is basically like a T3?
Yes.
So is it basically like your minimum
Okay.
propagation
So
delay?
again, the reason I mentioned this thing is that oftentimes people refer to minimum delay. And the point is that it's not the term we are using, so you don't have to care about it. You're not going to ask it. And the reason is minimum delay is inherently not very clearly defined, but generally speaking, minimum delay refers to what's the fastest my part will ever do. Okay? And that's not a value of interest. The value of interest is what's the fastest the output will change, not what's the fastest under some condition across the range of parts. When you buy parts, the data sheet says its minimum propagation delay is this, its maximum propagation delay is this. What it is saying is that across the parts you buy, across different operating conditions, sometimes the propagation delay may be, let's say, 10, sometimes it may be 12. It's the 12 that you are interested in, not the 10. Okay, so there's a band which is always given. So again, the two values of interest when it basically in derivative design are contamination delay and propagation delay. Minimum delay is an ambiguous term, just stay away from it. Okay, so now why do we kind of care about it? Delay through the combinational logic in itself is not of interest. What we really care about is when we are designing sequential logic, question which comes up is that will it operate correctly? How fast can I run my clock?
For the minimum delay, is it possible just to give it input and the input signal as the correction value? However, the output probably changes several times, and probably it changes for correction value and not correction value several times. Should we take the first correction value?
Again, forget minimum delay. I'm sorry I even brought that slide up. Okay. What you care about is contamination delay and propagation delay. If you hear the term minimum delay, from me or anyone else, ignore it. It's a useless quantity. Okay? It's a useless quantity. So you will see why contamination delay and propagation delay matter. The only reason I brought it up is because people loosely refer to that. Okay, but this again has no relevance as far as rest of digital design is concerned. So now imagine I have my sequential logic. I have combinational logic. I have flip-flop, and flip-flops which constitute my state register. So remember, the way this state system works is that at every clock tick, there is a new value which comes in, potentially a new value which comes into the state register. After a little bit of a delay through the flip-flop, which would be the propagation delay of the flip-flop, I will get a stable new value for the state now. So the current state has now changed to a new value. This will go through and then go through this combinational logic, and then after some time, the next state will become stable at its new value. And I have to make sure that this thing is ready in time by the time this clock edge comes. So when the next clock edge comes, I want to make sure that the new value of next state is all ready and good to go. So that's something that we need to ensure. And what that sort of translates into is a little bit deeper into how these flip-flops work. So what's happening in the flip-flop is it's waiting for a clock edge to come. When the clock edge comes, it takes the stuff at the input and stores it in memory, and then also puts it on the output. Now, if the data value were to be changing at the same time as the clock edge is coming, then the flip-flop will have a hard time kind of figuring out what, because just as the clock edge is coming, the data is changing also. And if it's a register, then I may have multiple data bits. So all flip-flops basically have two timing attributes which are of considerable importance. Because ultimately, again, they are making a decision at a point in time, and so there are two values which are of interest. One is called the setup time, so which you see out here. So the setup time basically refers to that each flip-flop will say that for the flip-flop to work correctly, the data must be stable for some time before the clock edge. Okay, generally setup time is positive. Okay, so it's basically saying that if I'm looking at a clock edge and I have a setup time, then it's basically saying that any changes in the data which you expect me to capture, so the new value of the data must happen before this time instant. If so, between this setup time and the clock edge, the data value should not change. Again, this is for the case where setup time is positive. There is also something called hold time, which is kind of the other side of the story, which is saying that, and by the way, I need some time to make the decision, so the data value should also remain stable a little bit following the clock edge also. Again, this is when hold time is positive. So what you're seeing is these two timing constraints that a flip-flop poses. It says, so this part is the setup time, and this part is the hold time. So it's basically saying around the clock edge where I have to make the decision, there is a window of time which extends from clock edge minus Ts to clock edge plus T sub h, that time window. So clock edge minus T sub s, clock edge plus T sub hold, this time window in which D must be stable. So a flip-flop through these two parameters basically defines a window of time around the clock edge in which the input data should be stable. If it is not, then correct operation is no longer guaranteed, and in fact some pretty weirdo problems can happen, which the effects called metastability and all, where the flip-flop output as neither a 0 nor a 1. You will learn about these if you go into circuits in future, but point being that as a designer, if you're given a flip-flop, you have to design something. One of the very first questions you should ask or look up in the data sheet is, what's the setup time, what's the hold time? Because you have to make sure that your overall design is such that for no flip-flop should the input of that flip-flop change in this window. In this window, the data must be stable. Flip-flops also have an additional couple of additional parameters, which are basically its contamination delay and its propagation delay. So now remember, the output of the flip-flop can only change as a result of the clock edge. So the propagation delay and contamination delay of a flip-flop are defined relative to the clock. So you have these two other parameters which you see out here, TDCQ and TCCQ. These are the propagation delay and contamination delay respectively between the clock and the output. So it's basically saying TCCQ says from the point the clock edge comes, what's the earliest time the data can begin to change. So you see, if I look at the output begins to change out here. And DCQ says what's the latest time it will stabilize, which you see out here. In between is a period where the output is unknown. It could be 0, 1. It could be 0 or 1. You don't know which one. Okay, so in the sense, it's not guaranteed to be correct. This particularly becomes important if you are looking at registers. So let's say a register state register, the old value was, let's say, all 0, 0, 0, 0, 0, let's say, for a 4-bit register. And the new state is, let's say, 1, 1, 1, 1. Now 4 bits have to change. They may not all change at the same time. So it's possible that from 0, 0, 0, 0, I may go to 0, 0, 1, 0, then 0, 0, 1, 1. Gradually the bits may change and ultimately settle at all once. So there would be a period of time in which any observer looking at the output will basically see incorrect or can potentially see incorrect values. So a flip-flop now, so unlike combinational logic, where we only had to worry about contamination delay and propagation delay, a flip-flop has these two other parameters, setup time and hold time. Setup time and hold time define a window of time in which the input to the flip-flop should be stable for the flip-flop to read the data correctly. Any questions on this? It's a bit of a tricky concept. Yeah.
What is negative TS?
I'll come to that. Any other question?
So why is propagation delay called TDCQ instead of TPCQ? I mean, what is the
Delay. I think it's just a convention.
Okay.
Yeah. Sometimes I end up using P also, so I will not penalize you, and even in the slides it's possible, but the book is using the convention D, will stick with that. In some future courses, you might see P for propagation. That's also common. Yeah. Any other questions on this? Okay. So the question which was asked out here is, I kind of kept referring that what if setup time is positive and hold time is positive, and kind of completely makes sense out here. In the homework, I have some scenarios where those numbers are negative. Now, the reason you may see negative hold times and negative setup times is that sometimes within the flip-flop, there might be additional delays on the clock. Maybe there is an internal inverter or buffer through which the clock goes through. So there is an additional time budget which comes up. The net result, details don't matter, is that sometimes you will see flip-flops which have values of setup time or hold time which are not positive. Now the way I like to think about it is focus on this one. Clock edge minus TS. TS is a signed number. So if TS is negative, that basically means that my input can keep changing until after the clock edge, but then it has to become stable. Okay, so I'll draw a picture on that, and let's say TH being negative means the reverse direction. So let's kind of look at an example out here. So let's say this is my clock edge. Okay, now let's consider a setup time of, let's say, 5 nanoseconds. That basically means that in this 5 nanosecond interval, things cannot change, so D can change before it, but here it should be stable. Okay. If on the other hand setup time is, let's say, minus 5 nanosecond, then it is saying until 5 nanosecond after the clock, D can keep changing, but then it has to become stable. Okay, so it just takes us in the other direction.
So if it's negative, you don't know how long before it'll stay stable.
No, if it is negative, all it is saying is that it can change up to this point, and then it should remain stable and for some time, and that comes from the hold time, for this clock edge to read the data successfully. Okay, and probably what is happening in a flip-flop like this is that internally, see, the hold time and setup time are defined relative to the flip-flop device that is given to you. But internally, if the clock has some additional delay before it reaches the actual flip-flop, then setup time could be negative. Okay? So that's what ends up happening. Hold time, same story. Normally, hold time is positive. So normally, we would say that it will remain, the data can begin to change after some time. So this would be my hold time. Okay. But if hold time is negative, so let's consider a flip-flop where setup time is minus 5 nanosecond and hold time is 10 nanosecond. Then that means in that flip-flop, this is the band of time of stability, where this is 5 and this is 10, right? So it's going from TS, the clock edge minus 5 nanoseconds, which means clock edge plus 5 nanosecond, through clock edge plus 10 nanosecond. Okay, so it should remain stable in this duration. Now, the setup and hold values will always be such that this stability time is something positive. Okay, so you would always see that going back out here, clock edge plus TH would always be later than clock edge minus TS, even for negative, even if TS and TH are negative. If hold time is negative, so let's say I consider a flip-flop which had a setup time of 10 nanosecond, and so this is S, this is H, setup time of S and hold time of minus 5 nanosecond. This is the hold time. Then what this is saying is, relative to the clock edge, so it should become stable at the edge minus 10 and remain stable through edge minus 5. And that would be the case with a negative hold time. And again, the condition which has to be met is that clock edge plus TH must be greater than clock edge minus TH, which is another way of saying is T sub H should be greater than minus TH. So another way of saying the sum of the two must be positive. Okay, otherwise it's an infeasible flip-flop. So in the homework, as you encounter those negative values of TS and TH, kind of keep that in mind. And what the homework problem asks you is, it gives you some data inputs and it asks you which flip-flop will you pick. So you have to kind of see whether if you make a choice of, there are 3 flip-flops there, A, B, and C. If you pick a flip-flop, would it set up and hold time be negative? So that's basically all that problem is asking you to do. So setup, hold time, very important concept. They could be negative because of additional delays inside the circuit path. But the basic concept is they define a period of time near a clock edge in which the data input should not change. If the data input changes, then the flip-flop will misbehave, and as a result, your sequential circuit will misbehave. Any questions before we go?
What is the square in the graph?
The square? Yeah, this is the region where the data has to be stable.
The what?
The data has to be stable.
Okay.
So it can change before it can change after it cannot change during it.
So it doesn't necessarily mean at that rising edge, it's taking the stability. It's still taking the data from that rising edge.
Correct. So what is happening is inside the circuit is sampling the data during that window.
From the stability or from
Here, it is going basically it is monitoring the data at this point. That's the region of stability. Whatever, by definition, because it's stable, that means the data has a particular value there. It's that value that the flip-flop will read.
how is it going to read into the future?
Because how is it reading into the future? Firstly, it's actually not reading. What is happening is that in this particular case, the data line, by the time your circuit probably has some delays in it on the data line. So by the time it reaches the place where the clock is doing its job, this data would have been delayed. So let's imagine I take this data line and I make it go through a wire which has a delay of 10 nanoseconds before the clock looks at it. Then it's fine, right? I mean, the whole data line would be shifted by that amount. So these negative values, I mean, it appears that magic is happening. That is, somehow the data out here is getting sampled even though the clock doesn't come into the future. What's really happening is inside the circuit, the data has been delayed before the clock gets to take a look at it. I mean, again, think of it this way. I have my ideal D flip-flop. Let's imagine I put out here a wire with a 10 nanosecond delay. Then it will appear as if the value that this guy is going to be monitoring is what was 10 nanosecond before the clock. Correct? So that's all that is happening out here.
What about when the stability is?
What about if the stability? Then that is as if I have my ideal flip-flop and there's a delay on the clock line. The clock is getting delayed. Okay, that's all that's happening. So an ideal flip-flop will have a positive setup time and a positive hold time around the clock edge. But because wires may have different amounts of delays, you end up with these, or there might be like buffer or inverter in there. So what you end up often is that setup time may be negative or hold time may be negative. But it's nothing, I mean, it's not as if you're suddenly doing time travel as a result. That's not happening. So these two are very important concepts. You'll see very soon in the next few slides. One of them affects how fast you can go, and the other affects whether your design is correct or not. And actually, much of the difficulty in high-speed designing modern integrated circuits, really boils down to this issue, which is answering these two questions. Is your design working correctly? And up to what clock speed can it work correctly? So, go ahead.
So when the stability is like before or after the clock edge, we have to change the delay of the clock.
No, you don't have to change the delay of the clock. Oh, when the
Yeah, if stability is ahead or behind the clock edge,
Hmm?
like on to,
Hmm?
you have to.
No, you just have to make sure your propagation delay and contamination delay of the circuits are correct. We'll see how that works out. Okay? But no, you are not going to muck with the clock. So again, very important point, which during the course of the previous homework I also said, you should never gate the clock. Okay, clocks are very carefully designed and you should not mess with them. Okay, but what you have to make sure is that make use of the knowledge of flip-flop characteristics and combination logic delays to make sure that the whole thing works correctly. And the entire very, very expensive CAD tools, design tools, which are catered towards just this problem. That is making sure that verifying the circuits that it would work correctly. So you'll ask questions like, will my chip work correctly at 1 gigahertz? Will it work correctly at 2 gigahertz? And you're trying to find what's the right clock speed. And of course, the real life is even more complex because delays of circuits change because of temperature. They change because of aging. Circuit, as it gets used more and more, slows down. Yeah, so there are also weirdo physical effects which happen. A chip which is running at 1 gigahertz today as its top speed, let's say, if you wait for 10 years, maybe the highest speed it can operate is 800 megahertz. Of course, when Intel sells you, they budget this thing into account that, a PC's lifetime is typically not more than 5 years, so they just want to make sure that over that 5-year window, things will work correctly. After that, all bets are off. So they kind of build in a lot of safety margin in their specifications. But all these things are subject to all these caveats: temperature, amount of age that it has. And even then, when you make chips, two chips coming out from the same fab line, designed the same way, may have very different top speeds. So one may only operate up to 1 gigahertz, other may be able to go up to 1.5 gigahertz. What do you think Intel does in that case? Huh? Yeah, they sell one as a faster device and make more money. Okay. Now, of course, the reality is fewer chips will work at a higher speed than the slower, so they charge more money. So it's all about managing the yield of production and all. Okay, very all economics at that stage. Okay, so moving back to our time story then. So what's happening now is, so we have our flip-flop, and given the setup and hold time, and for now in this picture, setup and hold time are both positive. So what you really have is that there is a window of stability. The flip-flop is sampling at the edge, but for it to sample correctly, it requires that the data be stable in that time period I mentioned, which is clock edge minus t sub s through clock edge plus t sub h. That's what is required. So for correct sampling, input must be stable from TS before the clock edge to TH after the clock edge. Again, assuming both of them are positive as in this case. Okay, so those are my two timing constraints. It should be stable in the purple region, which is the setup time, and in the green region, which is the hold time. Okay, output may change as soon as TCCQ after the clock edge. So this is the contamination time. So it's basically saying when the clock edge comes, the output can first begin to change as soon as this time, and no later than, that's the other timing constraint, no later than TDCQ, which is the propagation delay. So again, 4 time parameters which are of interest. So for a flip-flop, you'll be given that. Okay, so now let's go back and look at what does it mean for my complete sequential circuit. So now for combinational logic, we know that it has propagation delay and it has contamination delay. For flip-flops, we know it has setup time, hold time, propagation delay, and contamination delay. And for correct operation, we need to make sure that the input to a flip-flop is ready on time and remains stable during the region required by this flip-flop, right? So it cannot change too late, and also it cannot change too early, right? Because there is a region of time in which the new value of the state should be stable for the state registers to latch it correctly, to read it correctly. So that basically, as you can imagine, will lead to some constraints on the delays that we have: contamination delay and propagation delay and setup time and hold time. We cannot have arbitrary possibilities out there. So let's imagine that my combinational logic out here, the logic which is computing the next state, let's say it has 2 paths. There is a path which is the fastest path, which we have called min, and let's say there's another path which is the slow path, which we have called max. So this logic, this is the logic which is combination logic for next state, and possibly output also, but let's focus on the next state. So let's say inside this combinational logic has these 2 paths: a minimum path which goes from some input C through some output D, and it has a slow path which goes from some output A to some output B. So logic path with the minimum delay is out here, logic path with the maximum delay, the slowest path, is out here. and let's see what does it mean for us. So all systems, there are two constraints you have to worry about. One is the setup constraint and other is the hold constraint. So what's happening is the following. Let's imagine I look at this path, that at one clock edge, this flip-flop read a value from its input. That value propagates through, goes through the slow path, and it has to be latched by this flip-flop out here, right? So I have a path going from this flip-flop, goes through some logic, and this happens to go through a very slow path and hits this logic. Now, if you think about it, I have to make sure that the new value out here is ready on time, right? That's my setup time constraint. That is setup time before this clock edge, which is going to the bottom thing. The value produced by the upper flip-flop on the previous clock edge should have been processed and the new value be available out here. So what that means is that the propagation delay through the upper flip-flop, which is DDCQ, plus the combinational delay in the worst case, which is this propagation delay through this max logic, plus the setup time of this bottom flip-flop. All of that should be less than the clock cycle. This TCY is the clock period, clock cycle. Right? So it's basically saying whenever this guy, so let's say I'm looking at clock edge number 10. So so whenever clock edge number 10 comes out here, it produces a new value. That value has to go through propagation delay. It has to go through this yellow path, through the max, and then reach the D input of this bottom flip-flop, setup time before the 11th clock edge coming out here. So I have one clock cycle in which I have to accommodate the propagation delay of the flip-flop, propagation delay of the combinational logic, and the setup time of the successive flip-flop.
Why don't you have to worry about the delay until you start it, because on that same clock cycle, doesn't it?
We will worry about it later. Right now, see this flip-flop, the bottom flip-flop, only depends on this. Yes, the same type of constraint will hold true on this other path also, which goes from this C through D. Same logic will apply there also. The only thing is that one, because it's a fast path, TD max would be replaced by TD min. So the right hand side would only be smaller. So for this one, we only have to worry about the slowest combinational circuit, right? So that's why we are ignoring the top one, because if the bottom, if the path which I have shown, the colored one, if that meets the constraint, then the others will obviously meet the constraint. So propagation delay of flip-flop plus the worst case delay through combinational logic plus the setup time for the successive flip-flop, all of that should be less than the period of the clock cycle. If it is not, then my data will not be ready in time, and so my setup time for the following flip-flop will not be met. So, and we look at the maximum path. So again, going back to this question, why did I not look at this path, which is kind of going from the bottom flip-flop through the min to this one? If this inequality is met, then the other one is guaranteed to be met because min is faster than max. This kind of worst case path are called critical paths because they say how fast my clock cycle can be.
In general, are clocks always like immediate? Like, is there no like delay switch?
Say it again.
Clocks switch. Is there ever delay in real life? Or is it
Oh, you mean these edges?
like that?
Yeah, there is no such thing in physics as an instantaneous edge. It always takes some time. Okay, they are actually can be a nuisance. Again, in this course, you don't get to do it. Later courses, you do worry about it because during that time when the clock is rising or other signals are changing, funny things can happen. But usually they are in like fraction of a picosecond, so order of magnitude smaller.
So for say we take another course that the mean is going to always be less than max.
Yeah, so TDCQ and TS, I guess the assumption I'm making is all your flip-flops are the same in this thing. Okay. If they are not, then TDCQ is referring to the flip-flop at the beginning of your path, and TS is referring to setup time at the end of your path. Okay. If you think of your circuit, there are going to be a lot of pathways in it which start at a flip-flop, output of a flip-flop, and go through some combinational logic and end at input of another flip-flop. So this inequality, you have to look at the out for each such path, starting at a flip-flop, ending at a flip-flop. You are going to look at propagation delay of the starting flip-flop, delay through the combination logic, setup delay of the ending flip-flop, in case your flip-flops are not identical.
Why don't we include the whole time, like plus TH?
Well, why would you out here? If you think about it, in this particular case, all we are caring is that. So we'll worry about hold time separately. I mean, it was there for a reason. But right now we are worried that we are basically worrying about that I'm ready before that period of stability. Right? So separately we have to worry about that we remain stable for that stability reason. So right now all we are saying is I want to make sure that the new value that this bottom flip-flop should read should be ready before that required period of stability begins. Right? That's all we are worried about right now. So the name of the game out here is in your entire chip you have to find that one path which is this worst case one. Right? There is going to be you're going to look at all possible paths which start at a flip-flop, end at a flip-flop, and you are going to evaluate this inequality for all of them, and you have to look at the worst case one, which is another way of saying is I need to find the path which has the worst case combinational delay, assuming all my flip-flops are identical. And that one path, which is called the critical path, is the one which is going to dictate how fast your chip can run. Okay, because now let's say you discover, let's say your chip comes back, you were hoping it will work at 2 gigahertz, you put in a 2 gigahertz clock, doesn't work. Well, one thing you will do is you're going to dial down the clock. Because if I dial down the clock, then I'm increasing the left-hand side. And at some stage, that left-hand side will become bigger than the worst case right-hand side, and your chip will work, assuming from a setup time perspective. You'll still see the whole time issue later. So this constraint decides how fast your chip can go. Typically, the worst case path in a chip are those carry chains in our adders, or those chains to the adders and your multipliers. Usually, the arithmetic logic like that is often the critical path. Another source of critical path is when your chip goes to a memory and reads stuff. So it supplies the address, the memory does its work, the data output comes out. All of that needs to happen in one clock cycle, and that usually is another source of long delays. So critical path. So there are some very commonly known critical paths that one focuses on.
Even though averages are made of registers, we still consider it as combinational.
Yeah, they are combinational, right? You change the address, a new value will appear after some time.
So registers doesn't mean it's sequential.
Okay. Memories can take clocks also. So I guess I was referring to them as thinking of registers in the sense that at a clock edge something will happen. But you are right. Strictly speaking, not. They are pure memory. Strictly speaking, just a combination.
What is the T-slot?
What is what? Oh, the slack. Okay. Slack is the difference between the right-hand side and the left-hand side. Okay, so it is clock period minus the sum of all of these. It's basically saying how much margin do I have. And ideally, you would like to have some margin. The reason is that these, when your chip comes back, if you look at, it's not like, let's say I tell you, if you look at the flip-flops and you measure their TDCQ, they're going to be different. So it will actually be kind of some sort of a probability distribution. Usually will look like a Gaussian curve. There will be an average, some spread around it, and then you are going to pick a value for which you will say, 99.99% of my flip-flops have a delay less than that. So at some level you are going to, these numbers are not deterministic. They change from chip to chip. They change across temperature. They change with voltage. A lot of things affect them. So always you want to make sure that there is some margin that you leave so that unanticipated stuff can be handled. So that's what the slack is. If you kind of look out here, my clock from this dotted line to the left to this dotted line on the right is one clock cycle. TDCQ, the combinational delay, and the setup time. So whatever is the remaining time is basically saying how much time before the stability period is to begin and is my data ready. Okay, so this is one constraint. It basically tells you how fast the clock can go. The other constraint is for the hold time. So remember again, a flip-flop requires that the data input remains stable in the region clock edge minus TS through clock edge plus the hold time. So what I also need to make sure is that the data destined for the next clock edge doesn't arrive too quickly, right? Let's say I'm processing clock edge number 10. I need to make sure that because of some very rapid combinational logic, the data which was meant for clock edge number 11 does not arrive too soon after clock edge number 10, because then again I will have I'll see data changing very rapidly. So I want to make sure that the fast paths to my circuit are slow enough, because if they are too fast, their results may arrive too quickly, and a flip-flop which is still handling edge number 10 may see a data arriving before the whole time is over. So that's what's happening out here. So imagine that this bottom flip-flop changes its output. That change in output goes through this wire, through a yellow line, goes through this min, which is a very fast logic, and then arrives out here, while this guy is still in its whole time. So let's say I'm looking at a clock edge, same clock edge for both the parties. At this clock edge, what will happen is, if I look at the data line out here, what may happen is that it may change as soon as contamination delay through the bottom flip-flop plus contamination delay through this min logic block. And as soon as that happens, this D line can begin to change, right? I mean, so I'm looking at this clock edge. When this clock edge comes, then as little as TCCQ, the yellow wire will begin to change. And then as little as another TCCD, the contamination delay through this, D can begin to change. So what may happen is that if I look at the input D out here, look at the line D out here, it can begin to change as soon as TCCQ plus TCCD after the clock edge. And I want to make sure, and remember, this top flip-flop has a hold time constraint. It wants D to remain stable for a hold time period after the clock edge. So it wants data line D to remain stable for some time TH. So I want to make sure that T sub H is smaller than the contamination delay through this flip-flop and contamination delay through this fast path. Because if I don't ensure that, then what may happen is that D may begin to change too soon for this top flip-flop. So this gives me another constraint. It basically says that the sum of contamination delays, which basically tells me how fast, how soon after a clock edge can input to a flip-flop begin to change. I want to make sure that this thing is greater than the hold time, right? Because if it is smaller than the hold time, then this guy, the top flip-flop in our example, will latch in a wrong value.
What if the hold time is negative?
Then it's always negative. So hold time negative is good for you in this case, right? Because if hold time is negative, then left-hand side is negative, right-hand side is guaranteed to be positive, we are done. Okay?
So for hold time constraint, it has everything to do with contamination zones, and then for setup time, it's all about
Propagation. Absolutely. So setup time, you're looking at slow speeds, propagation. Hold time, you're looking at what's the fastest possible. You're looking for contamination. Does something strike you between this equation? What's the key difference you see between this equation and the previous one? In terms of dependence, like is there some particular thing that whose presence you see in this equation, but you don't see in this latter equation? Huh? Clock, exactly. The second equation has no dependence on the clock, right? This equation is totally. What does it mean? It means that if your chip is not working because of a violation like this, you can do nothing about it. You cannot slow down the clock, right? Because it has no impact on it. So this whole time stuff is actually particularly nasty. You better make sure that your chip doesn't have hold time violation before shipping it out, because if it does, then there is no. It's not like the first one where if it doesn't work, okay, I will live with a slower clock. Here it's not going to help you because it's independent of the clock. And the other observation which was made out here is if hold time is negative, then this thing is guaranteed satisfied. Okay. The problem is if hold time is negative, then setup time would be more positive. So what will happen is you will have a slower design than normal. Okay. So the strategy of artificially making hold time very negative can result in a very inefficiently slow design. So again, to kind of summarize out here, you have to worry about two things. One is the new value reaches all the flip-flops sufficiently before the next clock edge. And the second thing is that the inputs to the flip-flop do not get contaminated too quickly after the current clock edge. Okay. Both the constraints have to be met. The first one you can handle by slowing down the clock. The second one, the hold time one, there is nothing really that you can do about it, other than what? So how would you fix this problem? Let's say you see hold time violation. So one strategy is I pick flip flops which have a slower hold time or even negative hold time. What else can you do?
Increase the contamination of the main part.
Increase, yes. How would you do that? No, register. Remember, right hand side is all combination of it. So there's no register. Register is a flip flop. Huh?
Could you use like line up enough like knob gates or something that has some
Exactly. So I just slow things down, right? I mean, so I find the fast path and just put buffers there or whatever inverters, pairs of inverters, for example, right? Just slow them down until things work. But the problem is that is something you have to do at design time. You cannot do it after the chip has been made, right? Which is why this makes it this problem harder. You have to fix it before you ship that.
Did you say you made the whole time negative, the whole process will be slower?
Right, because if you think about it, if hold time is negative, then setup time. If you think about like there's a stability window. If it was about my clock edge, it's fine. Now making the hold time means I'm moving it before the clock edge. So the setup time will become more positive. So and if the setup time becomes more positive, then by our previous equation, this is going up, which means TCY will generally have to go up. Okay, so the solution that he was suggesting is the one which is I systematically identify the fast path and slow them down. Now the problem with that approach is sometimes the same combinational logic has the smallest contamination delay and has the highest propagation delay. Because it could be that my adder, when it's adding 0 plus 0, is very fast. When it's adding some other weirdo number combination, is very slow. So then adding the inverters or delays like what you're suggesting can also increase the TD max also. So it can slow things down also. So it's so the name of the game then is can I make sure that hold times are met, hold time constraints are met without sacrificing the speed of my circuit, okay? Because that has its own value.
Are there certain circuits that have like the same contamination propagation designs?
Very,
or like the same gate like gates?
short answer, no. It's very tricky to have, although it would be very useful to have. But no, I mean, if you look at your very basic gates, NAND gates and all, even they have different delays for different combinations. So it's very hard to pull that out. So, any questions on this before I move to the next slide? Okay. By the way, again, the problem set I've handed out kind of asks you questions on these, so you will get some. So, if you violate this point I've already made, if you violate the whole time, you cannot fix it by slowing down the clock. A solution is what was suggested out there, that I increase the contamination delay out here by padding my logic with additional stuff. Of course, another solution is get better flip-flops. So let's look at an example. Oh, go ahead.
As you said, another solution was what?
To get better flip-flops.
Yeah.
Yeah, flip-flops with shorter point time. Okay, so let's say I'm looking at same circuit as before, but this time we have numbers out there. So I've told you that the flip-flops has a propagation delay, contamination delay, and setup all 150 picosecond. They all happen to be the same. Hold time is 250 picoseconds. The maximum delay through the combinational logic is 850 picosecond, and minimum delay is 100 picosecond. So, question: is the hold time constraint met? So, hold time constraint basically corresponds to taking the contamination delay of the flip-flop and the shortest contamination delay, which is TC min, which is 100. So it's basically 150 plus 100, which is 250. 250 is, and remember our equation required that TH be less than TCCQ, TC min. So in this case, 100 plus 150, 250, 250, we meet it just about right, okay, no margin. What about the minimum cycle time? Now minimum cycle time is the propagation delay of the flip-flop plus the maximum propagation delay plus the setup time. So it would be 150 plus 850 plus 150. So it's going to be, so this is going to be 150 plus 850 plus 150, which is 1150. And this one whole time is going to be, I have to make sure that 250 is less than equal to 150 plus 100, which is 250. So this is met. And this is saying that TCY must be 1150 or slower. So the fastest clock that I can go is one with a period of 1150 picoseconds.
So it's okay if they're equal?
Yeah, I mean, it's basically saying no margin. Okay, any questions on this example? Typical questions around these revolve, or problems in real life around these revolve around to what flip-flop characteristics do I need? What should be the hold time for the system to work? How much padding to delay should I do if hold time is being violated? How much should I slow down the clock? All those kind of things. And sometimes for some problems, the answer is slow down the clock. Some other problems, some other timing violations, the answer is go redesign the chip, okay, which is typically with the hold time. Another example, consider a D flip-flop with setup time of 50, hold time of 40, the propagation and contamination delay are both 60, and is used to implement state register of a finite state machine. The next state logic has a propagation delay of 800 and a contamination delay of 50. You have to compute the setup and hold time slack. That means how much margin do you have before a violation occurs, given a clock period of 1 gigahertz. So firstly, 1 gigahertz corresponds to 1 nanosecond, corresponds to 1000 picosecond. So now let's look at, do you think this system would meet its setup time requirements? So can someone help me out? Let's look at setup. So why don't you just compute in How do I? Huh? Margin. Okay. Okay, anyone else? He says 90 for setup time. You seem ready, huh? 90, okay. So, those of you who didn't even make an attempt, so let me work it out for you. So, basically, we have to look at um, the propagation delay for the starting for the flip flops, that's 60, plus propagation delay through the combinational logic, 800, plus setup time, which is 50, that's 910 picosecond. 910 is less than 1000, so our clock is sufficiently slow. I can make the clock faster a little bit by 90, so roughly whatever 9% faster and still be okay. So that's the setup time. So so we have 90 picosecond slack. What about hold time? $70 picosecond. So that is correct. So hold time, we look at the contamination delays. So we look at the contamination delay of the flip-flop, which is 60, plus contamination delay through the logic, which is 50, which is 110, and it is greater than the hold time, which is 40, which is good too. We have a 70 picosecond slack. Okay. So that's this example. The book has many examples at the back, so I would strongly encourage you to work them out. Okay, I didn't realize I had the solution there. So, okay. Another bit of a nastiness which comes in real life design is that the clock does not reach the different flip-flops at the same time. So think of it, what happens in your system. There's a source of clock, and from that source of clock, wires run to the different flip-flops. The length of the wire from the source of the clock to the input of each flip-flop is not exactly the same. So by the time, if you were kind of an external observer and you were looking at the clock, same clock edge, supposedly the same clock edge arriving at different flip-flops, they don't arrive together. There's a tiny separation between them. So for example, in this case, what's happening is that the clock edge arrives at the top flip-flop a little bit later. There is a little additional delay it sees, T sub k. This is called the clock skew. So it's basically, if I'm looking at a particular clock edge, it might arrive at, let's say, time t out here, but it will arrive at time t plus T sub k out here. And that messes things up additionally. I have to factor those in also. So if you think about it, this clock edge can work in your favor or can work against you. If I'm looking at the setup time, and so in this particular example, the fact that this upper flip-flop sees the clock edge arriving late, it is bad for us because it's starting out late. Okay, so what will now happen is I have to say tk, because I'm starting out late, plus the propagation delay of this flip-flop, plus this long propagation delay, plus the setup time should still be less than the clock cycle. So this tk is increasing the right-hand side, which is bad for us because if I didn't have any margin, this inequality may not be satisfied. Likewise, this thing can also, a clock skew can also help or hurt us. So in this particular case, if I look at the hold time requirement, the hold time, what is happening is that I'm looking at the fast path. So I'm looking at TCCQ, which is out here, plus TC min. And remember, what is happening is this guy started early because this guy's clock edge came before this guy. So I also have to subtract TK. And that should still be greater than TH. So again, in this case, skew is again hurting us, because if skew is large enough, if this little delay out here is large enough, then this bottom inequality can also become unsatisfied. Okay, so skew can hurt us. What if it was the other way around? Let's say if this additional delay, if instead of being on the path to the top flip-flop, if it was for the bottom flip-flop, would it be beneficial? Would it hurt? Would it? So I'm basically saying, let's imagine the situation where this guy was out here. What if bottom flip-flop had the skew? That is, it received the clock edge later. Yeah, so basically you can think of it as, in that case, the signs of PK will flip, and so that would be helpful. So this kind of goes back to another way to potentially handle our problems, which is deliberately add the skew to the clock inputs of flip-flops at the right place. But you have to be very careful, because in this example, if I add skew to the clock input of the top flip-flop, it's bad for us. If I add it to the bottom one, it's good for us because I can run the clock faster and I can read the whole time better. So clock skew, because of this wiring, is another issue. Wires have delays. Wires have significant delays. Ultimately, the signal, nothing can travel, information cannot travel faster than the speed of light. So once you are into picoseconds and tenth of a picosecond kind of regime, even speed of light matters. Okay, I mean these are superstructural delays, and wires are not just transmission lines. Wires are RC resistance and capacitance, so they take even more time. They have big capacitance. They take time to charge up. So you have not just a standard speed of light delay, but you actually have to worry about all this charging, discharging. So the wires can have significant delays, and they can cause you problems. But so clock skew is something which kind of throws additional complications when you are doing this this hold time and setup time analysis. Okay. So now let's repeat our previous example, the same example, but now we are assuming that the clock has a skew of 75 picosecond. Okay. So what will happen in this particular case is that, and we don't know which direction the skew is, so we have to kind of prepare for the worst case. So what happens is, what was my slack previously was 90 picosecond for the setup time. Now it will be reduced by that much. So I will have less slack available. And likewise, the hold time slack would also go down. In fact, the hold time will be violated. So effect of skew, in the worst case, depending upon where the skew goes, the skew basically reduces the margins you have, and that can cause violation. So part of the reason we leave the margin or the slack is to take into account that the delays through this clock network, by the time clock reaches, is very hard to predict. They tend to be very complicated to analyze. And again, given that so much is riding on the speed of the chip and correctness of the chip, there are very fancy tools with very sophisticated algorithms whose sole purpose is to take your entire chip and do all this timing analysis for you. But what is more important for you is not kind of the calculation part, those are straightforward equations. It's really kind of getting a feel of what is happening, because so that when you are designing, you can take the right actions behind it. Okay, what happens if one kind of delay, one kind of problem happens versus the other? That's really kind of the main thing to take away from out here. So from what I'm told, by the way, I mean, even though I teach this class, I don't make circuits. Okay, I mean, there are other professors who work on it. What I understand though is that currently in the industry, hold time is actually the problem. Okay, I mean that's it's very hard to kind of predict. Okay, so for the setup time, there are very fancy circuits. Okay, what they do is they put in additional circuits on the chip which monitor to see if errors are happening, and if errors are happening, they go and tell the clock to slow down. Okay, so all of that happens automatically, or they tell the software that repeat the instruction. Okay, so setup time, there are all sort of tricks you can do. Whole time, the problem is that you are trying to detect how fast is something, and that's very hard to sense. Okay, how slow is something, what's the longest delay, you can design sensors, detect it, stuff like that. How fast is something in the best case is very hard to predict and very hard to detect. So hold time violations, hold time problems are just really, really nasty.
What is the limit on the slack that you can add for
None. I mean, you can.
like when would it be not an advantage anymore?
Oh, you mean skew or slack?
Excuse me.
Sorry, skew. Yeah. So obviously, if, as you can see, if I add skew the wrong way, it can actually make some of my things worse. In this particular case, 75 picoseconds skew kind of caused me to lose my slack and some for the whole time. So it was clearly bad out there. But skew can be judiciously added. Skew can be a little bit of a tool for you to manage these things. Okay, there is no particular number. It's really a tool in your arsenal. But as you can see, we are talking about delays and all which are sort of pretty tiny. So you're looking in, you're in the realm of picoseconds, tens of picoseconds. That's where you're playing.
How do we know whether to add or subtract skew in these two cases?
So, okay, so what happened in this case is we are looking at the worst case. So we are basically saying, oftentimes when they give the skew, like in this example, what they're saying is if I look at two flip-flops, one guy may receive the edge up to 75 picosecond earlier sometime, or may receive it up to 75 picosecond later at other times. So the skew is not even in one direction in this example, which is why we took the worst case for both. Normally though, what will happen is once you know precisely the skew, then it would either add or subtract depending upon the topology, and that was the case, for example, out here where we were adding it in one direction and subtracting it in the other direction. So in this case, we were told precisely that the skew is only here. That is, this flip-flop is always after this flip-flop, the clockwise. But oftentimes you are just given that, make sure that you are able to handle a skew of whatever, 10 picoseconds. Then you have to consider the worst case. Any flip-flop can be behind or ahead from the other. Okay. Let's look at this one. So I have 150, 250, and this is again the previous example, but now we have thrown in a skew of 100 picosecond. Is hold time constraint met?
Is the TK exempt for both?
Yeah, you have to consider worst case. So hold time normally is the contamination delay. So it's 150 plus 100. And I want to make sure that's large enough. So normally it is 250, which is just equal to 250. But now I have to subtract 100. And so I have violations. For setup, I have to take the propagation delay, so it's 150 plus 850 plus setup time, which is again 150, and then again we have to take the worst case, so I'm going to add the skew, which is 100, so it becomes 1250, and so the minimum clock cycle time will be 1250. So again, in this particular, so if I don't tell you, like in this particular case, we were really not given any other details. There is no circuit given to us, right? So the TK is really referring to that you have to be prepared. Any flip-flop can be ahead or behind. So you're really looking for a worst case. let's look at this example. So I am given this state machine. So firstly, what does the state machine do? Anyone? Yeah, count up by 1, right? I have a bunch of full adders and I'm adding a 1 out here. Okay. So it's a counter. Okay. And what we have to find, we are given the details. So assume that contamination delay for full adder is 10, propagation is 30. So minimum clock cycle between flip flops is 10 picosecond because I can go within same bits, and maximum time between flip flops is through 16 of these, so which is 16 times the propagation delay, which is 480 picosecond. Now assume that, so that's what we are given. So through this add 1 circuitry, my propagation delay is 480 and my contamination delay is 10. Assume for the D flip-flop, we are given that contamination time is 10, propagation is 20, setup is 20, hold is 10. Is the hold time constraint met? So to do the hold time constraint, again, remember contamination delays. So our contamination delays are 10 picosecond plus contamination delay out here, which is again 10 picosecond, and that is 20 picosecond, and we have to make sure that this is greater than the hold time, but our hold time is 10 picosecond. So I have a problem out here. Okay. So I have messed up. Sorry, I'm sorry. It should be greater than. Okay, so I don't have a problem. I was looking at the wrong one. Yeah, so hold time is 10. My delay should be more than that. So this is greater than X hold time, which is fine. So I don't have a problem. Okay, next one. What is the maximum clock cycle time? Clock cycle time, we are going to look at propagation delay, which is 480. Propagation delay of the flip-flop, which is 20. And setup time of the flip-flop, which is 20, which is 520. And that is going to give me the clock cycles time I can sustain. Can a skew of 20 picosecond be tolerated? So what were our margins? Well, so firstly, a skew of 20 picosecond, I can certainly tolerate it here. I can just slow down the clock. So the issue really is in terms of the hold time. If I go back to the hold time, I had only a 10 picosecond margin. So a skew of 20 picosecond cannot be tolerated in this case. So the answer to that, no. What can we do about it? So I certainly cannot slow down the clock. That doesn't help with hold time at all. So what would you do? Well, in this particular case, you'll have to redesign the flip-flop, as in get a flip-flop which has a higher hold time. You can reduce the clock skew. That's another option. We had a margin of originally a margin of 10 picoseconds. So if I can reduce the clock skew by 10 picoseconds, from 20 to 10, we will be in shape. And what that means is that you will rewire the clocks. So clocks are distributed all over the chip using a network of wires. So you are going to reduce the delays in those wires. The way to reduce delays in wires is to fatten the wires or whatever, just make the wires faster. So you're going to do that. So that's another option. And neither one of these things are really practical because basically in either case it means you have to go back to designing the chip. You could also, what you could do is you can add, this goes back to the answer which was given earlier on, which is I can go back to add 10 picoseconds of additional delay before each flip-flop. So I kind of just pad my delays. I could do that, but it will slow down the clock because when I add 10 picoseconds of delay, then it will also affect my critical paths also. So that will increase the before each flip-flops. It's going to also affect the timeout here. Okay, so in summary, delays are a nuisance in digital systems. Propagation delay and contamination delay are the two things which characterize combinational delay. For flip-flops, which are at the heart of all sequential logic, you have two additional things to worry about: setup and hold time, which together define a period of time in which data should not change. And then the rest of our issues, the setup time constraint and hold time constraint, really revolve around that we have to make sure these two equations are met. Clock skew affects both, and if you are given precisely where the clock skew is, then you can play better games, but otherwise you have to account for the worst case out here. And what happens when you violate these setup and hold time? So I mentioned earlier that some pretty awful things happen, and they are called metastability. So what happens is the following. This is a picture where the data was supposed to go from some particular logic value to some other logic value, but the designer did not pay attention. Some setup or hold time were violated, and what you would see if you were to put an oscilloscope, those who have never seen it, it's an instrument to look at electrical waveforms, you would see that the output now is just kind of oscillating and all. There are these phenomena called metastability, where if you want to monitor the output voltage, it will go into some realm where you can, it's neither 0 nor 1, it is sitting kind of somewhere in the middle, and it can spend a lot of time there. And when metastability failures happen, essentially your computer crashes. So what they do is they design these things so that the likelihood of violation happening, and therefore likelihood of metastability happening, is longer than other causes which will bring the computer down. As in, there are also other issues with software bugs, for example, or just other outages that happen. So there's no such thing as there's no such thing as it will never happen. It's just that you can, the designers across circuits and sort of logic techniques, make sure that it happens rarely enough.
I don't know what's happening there.
It's basically you were expecting waveform to be high, and then it goes into this oscillation stuff. This is not which should ever happen in a digital system. Digital system voltages are either corresponding to 0 or logic 1. What you're seeing out here is it's some jumbled voltage, which is neither 0 nor 1.
So it's supposed to be a straight line, so the green line?
It's supposed to be a straight line or a clean transition from 1 to 0, right? So it's spending a lot of time in this middle zone, just oscillating away. It's not a digital system during that time. It's neither 0 nor 1.
What's the yellow?
It's the original clock. It's a different signal. It's a clock. Either that, or I'm just looking at maybe the original. I think the yellow one is the input to the flip-flop, and the bottom one is the output, where supposed output, which should have been just a delayed version of the input. It got into metastability.
Can you go back to the example?
Which example?
The
Oh, the counter one? Okay. Here we are.
Can you explain
These numbers? Oh, so for the full adder, we are assuming that the contamination delay is 10 and propagation delay is 30. So if you look at now the whole full adder, so it has 16 bit of inputs and 16 bit of output, and we have to find its contamination delay. So if you recall, contamination delay is the minimum path between inputs and outputs. Minimum. So I take all the paths, I calculate each one of their contamination delay, and I take the shortest one of that. In this one case, for example, the path which goes from input here to the output out here has a contamination delay of 10, and that would be my shortest one.
that is not times
That is this guy.
no, I mean the 11. It should be 16.
This one? It's basically saying there are 11 more out here. 11 and 5 that I have drawn. Okay? So it's total of 16. Any other question? Okay. So I think what I'm going to do is I'm going to stop out here. There's another topic I want to go under the hood of flip-flops, which I won't start, so no point. So next lecture is going to be the review. It's the final lecture. So if you have any problems that you want me to take care of, send me an email.